Good evening, we're here with Can We Do That Some More, the more relaxed counterparts to the main Can We Do That series on my channel. Today, we're taking a look at solving second order differential equations manually. And if you don't know what I mean when I say solving them manually, because that's not really a traditional way of talking about it, I do have a video on that. The main Can We Do That video released 3 days ago, and a link to that video is appearing on the screen right now, so do check that out. And it's worth noticing, as always with these videos, we're covering things you don't need to know for the Maths A-level exam in England. So don't worry about this if you're trying to revise for any of those exams. This video is for extension purposes. And as always, here are the questions that we're going to be trying, but you are welcome to pause the video and have a go at them yourself. I'm providing this video as a way to give you questions to try that you might not easily be finding in textbooks yourself. So let's solve these problems, and it's worth noticing, as I said in the wording of the question, we're going to solve these without using an auxiliary quadratic equation. We're going to do it without guessing that y equals ae to the lambda x, which is what you would normally do in both cases, and that's in some ways weird because that is definitely the quickest way of solving these. We're doing it effectively the long way, but a way that's quite fun. But therefore, it's worth noting that in many ways, this is a terrible idea for a video, but as I feel like I've already got plenty of videos on this channel that already focus on specifically what you need to know for an exam, I feel like I can get away sometimes with just having videos that I'm doing for myself, for my own enjoyment, and this is one of them. But just do note, don't do the approach we're showing here today to solve these things in an exam. This is not the right way of solving them. Well, it is correct, but it's just not the best way, I should say. So, just like we showed in that previous video, showing this more convoluted way, you look at the number in front of the y, think of two numbers that multiply together to make it, and then also at the same time, those two numbers have to add together to make the number in front of dy dx. So, just like you would normally do when trying to factorize a quadratic, but we're not writing quadratic because it's not a quadratic, sort of. But anyway, two numbers that multiply together to make minus 28 would be minus 7 and plus 4, because they would also add together to make minus 3. So therefore, I'm going to write it like this. You could technically choose to have the minus 7 and plus 4 bit the other way around. And you would be fully right doing that way as well. You would get the correct answer in the end, but your method will look different to mine as a result along the way. But it doesn't matter. So if you did it that way, that's cool as well. Doing this means I can factorize 4 out of the third and fourth terms. So that'll leave me with a dy dx minus 7y. And also, the first and the second term are secretly just dy over dx minus 7y differentiated with respect to x. Which means I can now do a substitution because I see that dy over dx minus 7y appearing everywhere. So I can tidy things up by covering it up with a new letter. So let q equal dy over dx minus 7y. Because that means we now have dq over dx minus 7, plus 4. Let's deal with that. There we go. I saved it just in time. Plus 4. Q equals 0. And that is a new differential equation for us to solve. It's a first order one, so really a lot nicer than what we were beginning with. And you have a couple of different choices, either separation of variables or treat it like a first order exact equation. I'm going to do separation of variables, because why not? So moving the 4q onto the other side, dividing both sides by q, and then integrating both sides with respect to x. The right-hand side would integrate to minus 4x plus c, and we don't need an integration constant on the left, because you only need to put it in one place when integrating both sides, but that would integrate to ln q. You could put the modular sign around the q inside there, but it doesn't matter, because we're immediately going to get rid of the ln by doing e to the power of both sides. As always, though, with these sort of things in separation of variables, we don't like the plus c being in the power there. So you could then split it up using index laws and then rewrite e to the power of c as a new integration constant, like, I don't know, D, capital D is what we're going to do. So it's going to be Q equals e to the minus, not yet, D lots of e to the minus 4x. There you go. Nice. But Q was secretly dy over dx minus 7y. So therefore, that's a new differential equation to solve. And this would be a first order exact differential equation, so we need an integrating factor. We don't have a choice this time. So it's e to the power of the integral of minus 7 with respect to x, which of course is just e to the minus 7x. You could put plus c in there as well if you wanted, but it really doesn't affect these questions. It just means you have to write out more, but doesn't change the final answer whether you do or don't include a plus c. So multiplying both sides of the differential equation by the integrating factor, as is standard for first order exact equations. We get that. And then the right-hand side, e to the minus 4x, is being multiplied by e to the minus 7x as well, which of course does become an e to the minus 11x. But at this stage, we also might want to integrate both sides of the differential equation. And if you do that, the left-hand side, because of the way first-order exact equations work, after you've multiplied by the integrating factor, you already know the integral of that with respect to x will just be y multiplied by the integrating factor. But we haven't integrated the right side yet, so therefore I should write the correct notation to imply that I need to do that. So if I was to then integrate the right side, we'll get the left still being the same as it was, but the right being minus d over 11 lots of e to the minus 11x plus a new integration constant because we've integrated a second time here. So therefore, we'll write plus b. And the last thing we've got to do is multiply both sides by e to the 7x to get rid of it from the left-hand side. Or to get rid of get rid of e to the minus 7x on the left-hand side by multiplying by e to the positive 7x. So if we do that, the e to the minus 11x will become e to the minus 4x. And then we'll also get a b e to the positive 7x as well. And we're almost done. The last thing we need to do is just tidy up that integration constant in front of the e to the minus 4x, because we could just write that as a e to the minus 4x plus b e to the 7x by saying let a equal minus d over 11, so it looks a bit more neat and tidy. And there you go. We solved it. Definitely the long way, but it's quite cool. I like this way because it shows why do we have the e's, why do we have the integration constant of a and b, all that stuff. So there you go. Definitely not a way to ever do an exam, but I found it fun. So there you go. Hopefully you did as well, because we're going to do it again on this one as well. So this time, no choice. It's repeated roots, minus 9 and minus 9. So minus 9 dy dx, minus 9 dy dx, plus 81y equals 0. And then we can factorize minus 9 out of the third and fourth terms. And then the first two terms are secretly just dy dx minus 9y differentiate with respect to x. It's the same sort of pattern. Surprise, surprise. Let r equal dy over dx minus 9y. So therefore we have dr over dx minus 9r equals 0. Which again, going to solve. I'm going to skip a few steps because it's just very similar to what we had before. So you can rearrange to get this positive 9. There you go. And then we can integrate both sides with respect to x, which will get a ln of r equals 9x plus c. Cool. And then we can do e to the power of both sides, which will end up with e to the power of 9x. Would be plus c, but I'm going to immediately write the plus c as a plus d out the front of the e instead, because now creating more room, we can now undo the substitution to end up with the differential equation that you see here. Cool. So we're going to have to use the integrating factor again. That's just going to be e to the minus 9x. And so therefore multiplying both sides by it means I'm having to write loads of stuff out. Could have skipped this step, to be honest. That would have been much nicer for me. But it's always good to write your working out, isn't it? And interestingly, the right-hand side will just become d. That's what makes the repeated roots interesting, because this sort of effect will always happen. That means when you integrate both sides with respect to x, the left will become y lots of the integrating factor, and the right will become dx plus b. There you go. That means that we can now just multiply both sides by e to the 9x, which explains why you have that ax. I really should have used the letter a there, shouldn't I? That was silly. I didn't. Never mind. Dx plus b, lots of e to the 9x. That's why you have that ax plus b style thing out the front. So there you go. That's a couple of questions. Hopefully you had a go. Hopefully you have fun doing it. And if not, well, you just watch me doing it. So there we go. Spectator sport for fun. Hooray. So that will do us for today's video. And if you found this fun, then there's a link to a playlist of the entire Can We Do That series so far appearing on the screen right now. You should check out my Prove It series as well, because we prove a lot of the things you learn in the Maths and Further Maths A-levels, so do check those out. Remember to subscribe, like this video, and turn notifications on.